Uh, am I audible? Hello?
Yes, I can hear you.
Yes, sir. Okay, so good evening and a very warm welcome to our speaker and participants joining us today. On behalf of the Department of Electronics Engineering, MITS Deemed University Gwalior, I feel honored to welcome you to day two of the AICT sponsored Atal Online FDP on emerging frontiers in quantum technology and communication, being scheduled from 15th to 20th December 2025. Once again, I request all participants to please kindly keep their microphones muted and use the chat box for any technical queries. Uh, for today's session, we are pleased to have Mr. Laksh with us. Uh, Once again, good evening, sir. Welcome and thank you for joining us. Yesterday, we had the opportunity to attend your lecture on quantum machine learning, which was highly engaging and rich in knowledge. So, all the participants are eagerly looking forward to your lecture today. So, sir, over to you, sir.
Thank you, Dr. Mukesh. Can you see my screen?
No, sir. Yes, yes. Now it's yes, sir. Now, yes, sir. Now it's visible.
Okay, is it visible now?
Yes, sir. Yes, sir.
Okay, great. So the topic for today is quantum simulation, and quantum simulation is a big field. It's a big field even before quantum computing started. So quantum simulation is about simulating quantum systems on computing machine. These could be classical computers. This could be large clusters of computers and supercomputers. And now we are tackling this problem with quantum computers. So we will study, or we will go through the topic quantum simulation in that context. And beyond that, general reference to quantum simulation also includes other methods where quantum computing is applied to perform, let's say, Monte Carlo simulations or scenario simulations or analysis, etc., on really complex scenarios. But we are not considering that as a part of this topic. We are focused on using quantum computers to simulate quantum mechanical systems. That is the background of this session. And now I'm going to start. So the very first question that we ask is why should we use quantum computers for quantum system simulation? And to explain that, we will refer to this chart. What this chart shows is, let's we have to simulate systems like the ones that are shown here. This could be a protein, this could be a large molecule, this could be a small molecule, or this could be a very interaction between electrons inside of an atom. So what we are doing here on this x-axis is we are zooming in into the system and considering really small parts of the overall system to simulate, right? So it's like increasing the level of detail or increasing the level of granularity, going from more coarse grained simulation to more finer and detailed simulation. And when we go from more of a coarse grained simulation to more finer and detailed simulation of individual systems, we have to spend more computational resources. That's a big problem. Also, the accuracy that we need to do these simulations drops as we go to finer details, because we do not have those models and we do not have those methods to do those simulations on classical computers. The plot that you see here, these are different techniques of going from classical towards quantum, and the complexity of solving this problem using a classical computer is of the order of n factorial, where n is the number of electrons that we are trying to simulate in this quantum system. So n factorial scales even faster than exponential. So it's not feasible to do it on a classical computer. Then progressively we see simpler methods or more classical methods, but they are also quite expensive in terms of their complexities. The idea to do quantum simulation using quantum computers can be broken down into two segments. One segment is with whatever quantum computers are available in the near term or today and in the next few years, where we make hybrid systems of classical AI, classical high performance computing, and current generation quantum devices. And we use them to effectively make our calculations both more accurate, as you see, compared to semi empirical methods or DFT methods, and also faster as compared to CCSTs. So we want to get CCST level accuracy, but within the speed range of semi empirical and DFT. So this is the whole background. The second generation or the fault tolerant quantum computer will give fastest results at the best accuracy level, but that would require error corrected qubits, which are done over the course of next few years. That is the overall background. Now the question is, why should
हा
we use quantum computers to do this? So the
ठेवलं
idea
ते चेक करू थांब.
lies in the physics of superposition and entanglement is a fundamental quantum property, and the atoms and molecules represent and are governed by the same rules. The data, which is in a quantum state, and the correlations, which are exhibited by entanglement, are exactly based on quantum mechanics, how the atoms and molecules behave. And the scaling laws of quantum systems and quantum mechanics and quantum computer are directly mapping to each other. Hence, we can, in the case as we saw fault tolerant quantum compute, we do not need exponential resources. We can do that with lesser number of computational resources, but with same accuracy. Uh, I would recommend that you take a few seconds to grasp through this. This is a lot of detail. But what I'm showing here is on the right, we see that as we increase the size of a molecular system, the classical resources that are required to simulate this system is really high, it's astronomically high. But the number of logical qubits that are required to represent that system is relatively low. It does not have the same exponential scaling. So on the right, we see the exponential scaling, and on the left, we see various industry use cases that can be possible if we are able to do quantum simulations at different scales, from electrons to molecules, protein, DNA, RNA, to larger molecules, and even to materials. So you can just take maybe 30 seconds to have a look at this, and I'll proceed ahead. Okay. So, what we are going to cover today is one of the techniques in quantum simulation using quantum algorithms, The technique is called VQE, or Variational Quantum Eigensolver. And the reason I have chosen that particular algorithm is because it is very similar to what we have already covered yesterday. The way to implement a VQE algorithm is very similar to how we had created a variational machine learning algorithm yesterday. And the high level structure will be such that the input is a quantum system that we intend to simulate. We will convert the description of the input into an energy operator, uh, which is called as the Hamiltonian. And that Hamiltonian, we have to let that Hamiltonian evolve such that we can get the ground state energy or the lowest energy configuration. And visually, you can see that the overall energy landscape is quite nonlinear. And the goal is to go from a higher energy state finally to the lowest energy state. And this lowest energy problem or the lowest energy state problem is one of the most fundamental as well as one of the most important problems in all of industry, because any kind of design of a material or a chemical or medicine or biomaterial, everything is based on using the lowest energy configuration as a calculation tool, and then use it for doing more sophisticated chemical or molecular calculations. So areas of application can be drug discovery, it can be materials and catalysts discovery, it can be energy and sustainability. It can also be materials for in specific industries like heavy industries, automobiles, aerospace, etc. So the quantum simulation is the biggest application sector of quantum computing today and at least in the next few years. And hence, at QpiAI, we are heavily focusing on quantum simulation as well. So now we will, in the next 7 to 8 slides, we will go point by point on the technical details of quantum simulation. I will be covering it at a high level today as compared to yesterday, because this is a more complex topic and we do not want to get lost into the details. So we will cover it at a high level. So what problem does quantum simulation solve? It will solve the problem of computing the physical properties of quantum systems. And that system will be governed by the Hamiltonian operator, as we have seen. And this maps to equation, which is a energy equation where H is the Hamiltonian operator and E is the energy operator. And as you see here, this equation is basically an eigen equation. And it is named after Erwin Schrödinger. It's also called the Schrödinger equation. It's one of the most fundamental equations in all of physics. So what you see is H is the energy operator, psi is our eigenstate of the system, and E is the corresponding energy eigenvalue. And the primary objective of quantum simulation is to find ground state energies. Once we build system for ground state energies, we can also tweak that system to calculate energies for excited states. And once our energy calculation method is set up well, then we can extend it to time evolution of a particular quantum system. And we can also look into getting more detailed analysis around the correlations that we are modeling. And point number 1, 2, 3, and 4 can be used to do a lot of industry linked use cases like reaction energies and phase transitions. Just give me a minute. Yeah. So now the problem that we are solving, why are we not solving it with a classical computer? And the idea is really straightforward. Let's take a two-level system. right? So a two-level system, electron is a good example of a two-level system. And in that two-level system, the dimensionality of that two-level system is exponential in terms of the number of interactions that um n individual systems may do. So it has an exponential scaling. The state vector, as it is written in terms of the individual bases and combined to create the global state, you'll see that it has an exponential scaling as well. To do the classical simulation of these quantum systems, the memory to store the state, let's say, and let me take an example to make this more intuitive. Let's say I have to simulate a water molecule, right? So it's H2O. Now, the total number of electrons that we need to simulate, the memory that will be required to store the wave functions of those electrons will vary as 2 to the power n. And one of the methods to solve that system analytically and exactly by doing diagonalization that scales even more strongly. It's 2 to the power 3n. So, because of this exponential scaling, in terms of the dimensionality, in terms of the number of operations that are required, and in terms of the total memory footprint that it has, it's not feasible to solve this problem on classical computers. In fact, the interesting part is that at the very origin of or the conceptualization of quantum computers, quantum simulation played an important role, and it was one of the primary motivations to discover the feasibility of quantum computers back in early 1980s. And this quote is really famous from physicist Richard Feynman, where he argues that if we want to simulate a quantum system efficiently, or if we want to simulate the entirety of nature better, we'll need to make a machine that is quantum mechanical and run the simulations on those quantum mechanical machines. So, we understood so far what are the classical limitations for which we need to make quantum computing based algorithms for this domain. Now, we are going to systematically see how that is done. The way that it is done is by expressing our energy operator, the Hamiltonian, as a combination or a linear combination of these Pauli matrices. And these are the matrices that you already know in your initial study of quantum circuits and gates. So these are the Pauli matrices X, Y, Z and identity. And typically they are written by sigma X, sigma Y, sigma Z, or sigma I. Why is this important? It is important because these Pauli matrices, when expressed to describe the Hamiltonian, they are supported as a direct measurement on the quantum hardware. And these operations are naturally supported in the form of the pulses that we run on a quantum computer. These Pauli rotations are natively present. We will skip the details here, but what I wanted to show is that the Hamiltonian is constructed via a pair of interacting terms, right? So this P and Q represent the interacting terms, and we sum it over across all the interacting terms. And we see here we are having pairwise interaction, and then here we are also having interaction in terms of the local what should I say, the neighbors. Okay. So this is just an example. We don't need to understand this in detail, but the idea is that Hamiltonians are constructed to aggregate all of the interactions of our quantum systems. And several types of transformations can be used to convert our molecular or electronic Hamiltonian into a qubit Hamiltonian. The Jordan Wigner or Brevy Kitaev transformations are some of the examples of it. Right. So coming back to our point, let's say if we have a molecular Hamiltonian, we need to convert it into a qubit Hamiltonian. And once that molecular Hamiltonian is converted into a qubit Hamiltonian, we can use our quantum algorithm to find the minimum energy state by running an iterative algorithm. And we have already seen yesterday that how we were parameterizing the algorithm, and through the parameterization we were iteratively training and finding the best linearly separable boundary. Similarly here we will be finding the uh, lowest energy state. That will be our objective. So the problem is to find E naught, which is over all the possible wave functions or quantum states given an energy operator for that particular state. The system will find the minimum. Basically, the system will find that psi, which will minimize h, and corresponding to that energy operator, we will get an energy E naught, and that is what we want to identify. Final output will be E naught. This is the energy we want to calculate. Now, the one of the points that uh, why this is possible is because of this particular bound, which says that uh, the computation of the expectation value of h with respect to the state psi will always be greater than or equal to the minimum energy. It's a fairly straightforward uh, fact that of all the possible energies that can be calculated across the different states of psi for that energy operator h, it will be greater than or equal to the minimum energy, which is quite intuitive also. And it will be equal only when the quantum state psi is in a ground state. So this becomes a very useful tool for us to find the ground state energy because we can leverage the power of superposition and entanglement on a quantum computer and solve this problem. We will use a technique called as variational quantum eigensolver to solve this problem of finding the minimum energy state. And the trick that we use here is the same trick that we have seen yesterday. Instead of searching over all the possible states psi, we will parameterize the state psi with a vector theta, and then we will make a search in the theta space. So from a deterministic computation or a brute force, it goes on to a more of a variational structure where we can do parameter optimization and keep on changing the theta. And the rest of it you can follow from our discussion yesterday. We created an initial state get 0, applied our feature map in that case. In this case, it is our unitary operator that will be implementing the VQE algorithm. So we get the state psi of theta inside a ket, and the Hamiltonian, the way it is constructed, is by the same technique we have seen earlier. We multiply these coefficients, the complex coefficients, with Pauli matrices and define the energy operator. So the Hamiltonian is constructed, the parameterized circuit is constructed. Now what we need to do is we need to apply an iterative process and use a classical optimizer to find the optimal value of theta. Now this is how the loop runs. This is a description of what I have already told. We will prepare the parameterized state on the quantum computer. Then we will be measuring the expectation values, and using these expectation values, we will be calculating the energy. And we will keep on calculating this by changing theta by using classical optimization, unless and until we are confident that this is tending towards the minimum, right? And that situation is called convergence. Just think about it. We are just setting up the algorithmic steps, but one of the questions to ask is what CI values to use here, or what should be the unitary operator to build the parameterized circuit. So the case turns out is that there can be different types of unitary operators. Some are suited for specific kind of molecules, some are suited for specific kind of hardware, and it is a research area in itself of what type of unitary operators are suitable for what kind of applications. So if you are considering to apply quantum algorithms to some of your research in the simulation domain, this is a good problem to explore. So one of the special types of parameterized circuits, the ansatz, is nothing but a parameterized circuit. It's a name for that. So one type of ansatz is a hardware efficient ansatz, which favors shallow circuits, and all the gates that are used in this ansatz are compatible with the gates that are available on the hardware. But the issue with having a hardware efficient ansatz is that it does not fully capture the chemistry of that particular molecular system, and there may be a case where it gets stuck in a local minima. That is a problem. And another problem is the problem of barren plateau, where what happens is that in our cost landscape or the optimization landscape, you cannot find a minimum because the gradient saturate and that surface becomes flat. So to make it more visual, a barren plateau situation will come in when there are not these hills and valleys, or there are not enough uh, crests and troughs, but the surface becomes flat. So you cannot do that kind of a gradient based optimization. This I'll skip, and this I'll skip, and this is basically the challenges that I was just talking about. So far what we have seen is we can use the VQE as a algorithm or as a quantum algorithm to solve the problem of quantum simulation. We can do that because the scaling is much better as compared to classical algorithms, and there are various strategies that are needed when we build the kind of algorithmic structures to solve the problem. So now we will take hydrogen molecule as an example, H2 molecule, and the pipeline is what we have seen as a basic algorithm description. We will use the molecular geometry to create a Hamiltonian. From a molecular Hamiltonian, we will go to a qubit Hamiltonian. Then we will select the parameterized circuit that we need to construct. And after the parameterized circuit is constructed, we will apply it to the VQE algorithm, do a classical optimization iteratively, and then we can compare it with how it compares with other analytical methods. So naturally, the scaling of VQE is much better than classical algorithms. The challenges are only time limited, because as the algorithm scales, we need more qubits and more polyterms and deeper circuits. So one thing I would like to highlight here is the scaling of the algorithm is very optimal. It's good, And as the hardware scales, as we get more qubits, as we get systems that can execute deeper circuits, that is where we can really achieve a really significant advantage in the simulation of these molecular or electronic systems. So, this is the description of the algorithm VQE. And what I would like to do now is I would like to show a very basic example of. Can you? I have switched my screen. Can you see the screen?
Yes, sir, it is visible. Your collab is visible actually.
Okay, yeah. So, what I want to do is I want to demonstrate the working of VQE with a very simple example. Just like we took a very simple example yesterday to understand the underlying algorithm, today also we will take a very simple example to understand the underlying algorithm. And then using more sophisticated tools and libraries, you can, when you apply this into your research or into the domain of application that you are working on. So some of you may work on healthcare. Some of you may be working on materials. Some of you may be working on high energy physics. Some of you may be working on basic chemistry or computational biology, etc. Right? So people from these different domains can come in and they can use the quantum simulation as a solution to discover new kind of algorithms and build on top of it. So I will be covering the implementation without any library for us to look into the internal workings. Right, so I am starting now. Our primary objective is to find that optimal psi that given the eigenequation which is describing the evolution of our system, we can find the minimum energy. And the strategy to do that is rather than exploring all of the possible psi, we will be parameterizing our quantum state. And that quantum state, we can apply a classical optimization in a search and train our variational algorithm to find the most optimal theta. That is the larger picture. And in fact, if you see the diagram that I was showing yesterday here, that is in fact the diagram of VQE itself, where we do a state preparation, we do the the operator estimation for calculation of energy, we calculate the loss, which is basically given by the specific chemical system, the way we design the energy operator. And then we do iterative parameter optimization through that. So coming back, what we will do now is we will apply this on basic simple quantum system, and we will be taking hydrogen molecule as the basic quantum system. So what I'm doing here is I'm building everything on top of NumPy, and we will be applying the principle of variations to calculate our optimal theta vector. How to do that? As I've already told that we will be creating the Hamiltonian through these Pauli operators. And just as we had created different gates yesterday, I'm defining this I, X, Y, and Z operators as matrices. So I'll execute that. And I'm also defining the cron operator, which will be calculating the Kronecker product of two operators. If I input A and B, I will get the output of A cron B. The next step is to construct the Hamiltonian itself. And just as you had earlier seen that we were writing about the Hamiltonian structure as sigma over CIPI, where pi go from the Pauli matrices. This is an example Hamiltonian that we have created, where we have two interacting terms uh, in here, which is x0 and x1, two interacting terms here, which is z0 and z1, and we have two independent terms, which is one z1 and second z0. And these are the coefficients that we are using to based on our structure of the molecule, we determine these uh, coefficients. So looking through the code, what we have done here is we have applied the Kronecker operator, and through that we have created x0 and x1, we have created z0 and z1, and we have created the product x0 x1 and z0 z1, right? So this is a Kronecker product between itself, the operator and identity. Whereas here we are applying the product for the operator in itself, and that is what creates our interacting system. And we can define any arbitrary coefficient in the beginning, because over time it will change and it will become better as we iterate over the algorithm. So with that, our Hamiltonian is created. After the Hamiltonian is created, we will use the variational quantum algorithm to solve the problem. The very first step is what we will do is we will select an ansatz or a parameterized circuit, and use that parameterized circuit to create a quantum state and then do the iterative optimization. But before we do that, since this is a very small system, we are solving this eigenvalue problem analytically and seeing what should be the true solution. So the true solution should be somewhere close to this value in terms of solving the eigen equation. So we will keep it as a reference. Now what we are doing is we are defining this as the ansatz. We are taking a 2-qubit system starting from ket 00, then applying these set of gates on the 2 qubits, then applying a C0, where we can determine the control and the target, and then we are applying other quantum gates here as well. So what you see here, we are taking the parameters theta naught, theta 1, theta 2, and theta 3. These are the parameters, and it will create the parameter vector theta. This is the programmatic description of creating the RY gate, which we are using at different points, defining the C0 gate, and then creating the state ket 00, which is basically representing the ket 00 state, and then defining the ansatz here, which is this circuit. I'll execute it. The code is executed. And we are also defining the function to calculate the energy. And as you see, the energy calculation is fairly simple. We take in the state vector, apply the Hamiltonian operator, and after the Hamiltonian operator is applied, we multiply it with the dual of the ket vector, which is Brassai. So we have executed this as well. And now we can run the optimization loop through the parameter shift rule that we had briefly touched upon yesterday. So running this particular small system of VQE, what we see is that for this basic Hamiltonian that we created, the energy landscape, within the energy landscape, as we increase the number of iteration, the energy decreases. So what this shows is that our algorithm works. Algorithm works because iteration by iteration, the energy is decreasing. So we have done this on an arbitrary Hamiltonian. Now we'll try to do this on a hydrogen molecule. And we will be using the standard method of converting a qubit Hamiltonian, the molecular Hamiltonian to a qubit Hamiltonian, and applying by applying these different techniques. So this is the simplified two qubit hydrogen molecules Hamiltonian defined by this. How this comes up is basically through some knowledge about the transformations, which is not relevant at this point, but if you go deeper into the domain, that would become relevant. And we have solved for the exact eigen equation, and we get this as a result. After this, we will solve it using the VQE algorithm. So we were just doing everything that we have been doing in the last example. We are defining the energy operator. After we define the energy operator, we are running over the VQE loop by starting with the initial random theta vector, then iterating over the classical optimizer. And in each of these classical steps, we create the quantum state. We parameterize it with theta, and then we calculate the gradient with respect to the previous iteration, and that's how the loop runs. So if I see what happened when I ran the VQE circuit, again we can see that basically as the number of iterations increase, there is a smooth decrease in the energy value, which also indicates that we are able to solve our problem, or we are solve the system of H2 molecule for calculating the minimum energy state. Similarly, we can define a more complex system. Instead of H2, we are going with lithium hydride. And even here, we will run the same kind of execution. And we will see that even for this system, the VQ algorithm will work. Progressively, with iteration, the energy will minimize. Now, what happens in the VQE is that we have seen this for various kinds of small systems, but the latest and state of the art research that is being done in the domain of quantum computing today, applying it for industrial applications like quantum chemistry, discovery of novel materials, design of new catalysts for large scale industrial processes, simulation of battery chemistry, etc. All of this can be approached through the VQA algorithm, and it's a great area of research for you to be in, and create both educational interventions as well as some research outcomes that can lead to new intellectual property and also products from your side. So with that, I will stop, and I'll conclude my session. Maybe I can take a question or two, and we can conclude. I would like to, and before I conclude, I'll uh, just recall what we had seen yesterday. Was about the different algorithmic stacks and the quantum computer access that I was referring to. So, in that context, we are also working on building molecular simulation libraries on top of algorithms like VQE and also some other algorithms. And anyone who is interested to explore this area, please feel free to get in touch, and we'll see how we can work together. So, with that, I'll stop, and I can take up a few questions if there are any questions. Otherwise, we can conclude.
Hello, yes, audience, participants. If you have any question, please ask, or you can write your question in chat box. Is there any question?
So otherwise, if any question comes up later, I can answer them through email.
Okay, sir.
Somebody is asking to unmute actually.
Okay. Uh, just
Hello, am I audible?
yes, sir. Sir, you can unmute yourself.
Yes, am I? I have unmuted. Am I
Yes,
audible?
yes, 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 yes.
Yeah. Yeah. Thank you. Thank you so much. Good evening. Good evening, Professor. Thank you for the very enlightening lecture. Actually, I'm Dr. Sabyasachi Bhattacharya from Government of Assam, Barakville Engineering College, Sribhumi. I am working in the domain of quantum communications. So, in context of quantum communications, I would just be interested to know that you were showing some Hamiltonian representations during the beginning portion of your slides today. So in that actually you are representing some age parameters actually. So are those some time varying channel characterizations, or some might not be channel characterizations, but some time varying characterizations of any quantum fluctuating quantity, or exactly what do you mean by those?
Yeah, so this H actually represents the way the energy of our actual quantum system is varying. So let me give a classical intuition or an example. Let's say we are studying the motion of different systems, right? So we have different operators that we can measure, like velocity, position, momentum, right? These are physical properties that we can observe, right? Similarly, for these, let's say for a molecular system or an atomic system, we would want to measure the energy. And the way we measure this energy is by describing a operator, which is the energy operator, and this energy operator is represented by H. So it can be time varying also. Typically, when we work on time on the dynamics of a quantum system, the Hamiltonian varies with time. So Schrodinger equation can also vary with time, basically in the form of a differential equation. To simplify this system, to simplify the algorithm, I am sharing a static Hamiltonian of one single time instant.
Okay, and just one last small query from my end. When we are simulating these quantum states, actually, what is the present state of the art? Like, if we are taking a classical problem at hand, like my area is mostly a classical communications or a signal processing problem. So, in that case, have any recent tools come up where we can conveniently model our system to a qubit-oriented system? Or is it just like just as it was in terms of like representing it as qubits, but later on the processing at the backend is all classical, just a like a for show representation. How is it like that basically?
Yeah, state of the art in quantum computing is the kind of algorithms that VQE itself is an algorithm. So VQE and its variants are the state of the art when applying quantum computing to these simulations. Classically, there are methods like DFT, like density functional theory, as I was showing in the beginning, and other kinds of methods. The gold standard is called a coupled cluster method, which is a classical algorithm. But VQE is as accurate as coupled cluster method, but scales very well as compared to a classical algorithm.
Okay, sir, thank you so much. Thank you organizers. Thank you.
Yeah.
Anyone, if you have any question? Okay, I think there is no questions. Uh, okay, okay. Thank you, Mr. Laksh, for this interesting and knowledge enriching lecture. Thank you so much.
Yeah, thank you all.
Okay, sir. Uh, hello participants. We will now take a 20 minutes break, and after that we will begin our next session.